Welcome back, students, to Chem 101. My name is Professor El Hawari, and today we will be going over Chapter 4, which is called Bonds An Introduction to the Forces Within Substances. We'll be going over the 21st Century Chemistry textbook by Kimberly Waldron. So, again, every chapter begins with a story, and our story begins on page 93. So, if you have your textbook, turn to page 93, and it reads: In the 2002 film Die Another Day, James Bond faces off with villain Gustav Graves for control of a solar focusing device called Icarus. This device is so powerful it can incinerate anything, and Graves must be stopped before he uses it to take control of planet Earth. Icarus may seem like science fiction, but in fact, such devices, called solar furnaces, in the real world do exist. The biggest, most powerful solar furnace, see photo on page 94, is located in the sunny little French town of Odio on the border of Spain and France. At this facility, 10,000 mirrors focus the sunlight that hits them, and this concentrated sunlight is indeed powerful. In fact, no known substance can withstand the temperatures in the solar furnace, which can reach as high as 3,800 degrees Celsius. This chapter is all about the forces that hold substances together. We'll explore this topic throughout the chapter because these forces help us account for the properties of matter. So, in this chapter, we'll talk about bonds and forces. So, again, as we read in the introduction, solar furnaces that are shown here can reach temperatures of 3,800 degrees Celsius. That's very high. This temperature can actually melt iron. It's that high that it will melt iron. And diamond, which is, as we know, is a very tough substance on Earth, will even melt. It even melts at a temperature lower than this temperature, 3,500 to be exact. So let's talk about the forces. Now, the question is, why do substances melt at such different temperatures? You see diamond at 3,500, iron at 3,800, and the real answer lies in bonding. So, bonding, you can think of it as the glue that holds things together. So, again, we're going to explore forces that hold substances together, and we're going to cover the different types, and different forces cause differences in melting point. You can think of it as different glues. Now, the first thing we're going to talk about the octet rule. So the word octet, just like you can think of another word like octopus, which means eight. So eight is the magic number. Atoms interact with one another to gain stability. Some atoms lose electrons, and the other atoms are going to gain electrons. But at the end of the day, they have to have eight valence electrons. And we talked about this in the previous lessons. Noble gases, the last group of the periodic table, group 18 to be exact, are known to be inert, which means they are unreactive. They do not react with anything because they're very stable. Why are they stable, you might ask? Well, because they have an octet. They have 8 electrons in their last shell. So again, stability is related to the number of electrons in an atom, and it's also related to the atom's location on the periodic table. Depending on where the atom is, will dictate its behavior. So the octet rule, as we said, uh, every atom, every atom has a nucleus, and the nucleus is surrounded by the electrons. The first ring after the nucleus can hold a maximum of 2 electrons. The second ring can hold 8 electrons. The third will hold 18 electrons, and the fourth will hold 32 electrons. Every period on the periodic table, we are going to get a new energy level. So we're going to get a new ring every time we add another ring. And every element from left to right has more electrons than the element before it. Why? Because the atom has to be electrically neutral. And the outer level of the last element in each period is completely filled. We're going to talk about this in a little bit, but when, for example, noble gases have a completely filled outer shell, and that's why they are inert and they do not react with other elements. Now, if we look, the noble gases are in group 18 are helium, neon, argon, krypton, xenon, and radon. All these elements in group 18, because they have their shell is filled to the maximum number of electrons possible, so they're happy, they're stable, and they have achieved the octet rule. Electrons, again, as a continuation of the octet rule, all the electrons have the same mass and charge. The electrons have a mass of 0 and they have a charge of -1. The electrons differ due to their location in the atom. Electrons that are closer to the nucleus have less energy. They're sitting on a energy level with less energy, and electrons that are far away are sitting on a shell with a lot more energy. You can think of it as the rubber band example. The more you stretch the rubber band, the more you have energy stored. um, and the last thing, electrons are considered to be either core or valence electrons. Core electrons are close to the nucleus. Valence electrons are all the way far. They're all the way at the outside of the nucleus. They're the furthest shell possible away from the nucleus. So if we look here, this is the aluminum nucleus as an example. The first ring has 2 electrons. The second ring has 8 electrons. Now the third ring has 3 electrons. The first 2 rings will be considered core. You can think of this as an onion. And the third ring, the one that has 3 electrons, would be considered valence. So the core electrons are in the inside and the valence electrons are in the outside. The electrons that are responsible for bonding are the electrons on the outside because they could be easily grabbed by different elements and because they're not attracted to the nucleus as much as the core electrons. So again, valence electrons are the outermost electrons and the core electrons are located between the nucleus and the valence electrons. As we just said, the reason why certain elements participate in chemical reactions is because of their valence electrons. The valence electrons are involved in chemical reactions because they're farther away from the nucleus and they're less attracted to the nucleus. They could be either lost or gained in the valence shell. Core electrons, on the other hand, do not partake in any chemical reactions because they are attracted to the nucleus. If you remember, the nucleus is positive, the electrons are negative, so they are attracted to each other. But if the negative electrons is far away, it's not as attracted to the nucleus as core electrons. And the noble gases obey what we call the octet rule, which means they have 8. The magic number is 8 electrons in their outermost layer, and they have a noble gas configuration, which means they are fully stable, i.e., they do not participate in any reaction because they're very happy, they're very stable. Now, if you might ask, how do elements achieve stability? We are talking about the noble gases, how they are very stable. But what if we talk about an element like fluorine or chlorine or bromine? Are they stable? They are almost stable. Now, how do they achieve stability? They do this by either gaining or losing their valence electrons to try to be like the noble gases. Every element on the periodic table wants to achieve stability. So now the elements on the right, if you remember from the last lesson, elements on the right of the periodic table are non-metals, and non-metals tend to gain electrons, whereas metals tend to lose electrons to achieve stability. Now, there is something called the Lewis dot diagram. So, Gilbert Lewis came up with these diagrams, and it's a way to keep track of electrons, but not just any electrons, the valence electrons. You might be wondering, well, are the core electrons not important? They are important, but they're not important when it comes to reactions, chemical reactions. The electrons that make a difference are the valence electrons. So the Lewis dot diagram is a visual to show us how many valence electrons each element has. And then we can figure out, well, is the element going to lose these electrons to become stable? Is it going to gain these electrons to become stable? Or is the element already stable? For example, the element boron, which has the symbol uppercase B, has only three valence electrons. So we would put three dots in any of the directions. You could put it north, east, and west, north, east, and south, and so on and so forth. As long as you have three dots, this shows you immediately that boron has three valence electrons. And this diagram is called the Lewis dot diagram because the electrons are represented as dots. Also, they could be represented with X's. So you can see either dots or you can see X's. Now, the good thing as well about a Lewis dot diagram is that it shows us if an element has a lone pair or a lonely electron. Um, well, a lone pair is a pair of electrons in the Lewis dot diagram. So this, where my mouse is hovering over, this will be considered a lone pair. So these two electrons are sitting on top of the fluorine, also the electrons on the east side and the electrons on the west side. So these are called lone pairs. And now we have another electron. It's all by itself, and so the fluorine would want to steal another electron from another element in order to feel happy, in order to have eight, in order to achieve an octet. The lone pair, we have three lone pairs on fluorine. They're also called non-bonding pair because these electrons are not connected to another element. So that's why they're called either lone pairs or non-bonding pairs in our Lewis dot diagram. All right, and let's talk about the first and very important type of bond, which is called the ionic bond. Ionic bonds, well, why does an element participate in such a bond? Again, it's to become stable and achieve the octet of electrons, which means eight electrons. And you can think of the ionic bond like a glue or an attractive force that brings the atoms together. What's so special about ionic bonding is that it exists between a metal and a non-metal. So again, metals are found all the way to the left of the periodic table, whereas non-metals appear all the way to the right. Metals on the left, non-metals are on the right. When an element from the left of the periodic table reacts with an element from the right of the periodic table, an ionic bond is formed. That's different from covalent bonding. Covalent bonding occurs between two non-metals, two or more non-metals. So you uh, have elements to the right of the periodic table reacting with one another, and that's called a covalent bond. Let's talk about ionic bonding in details. If you have a magnesium atom, magnesium, as you know, is a metal. It's located on the left of the periodic table. When magnesium, a metal, participates in ionic bonding, it tends to lose electrons. Metals lose electrons. When the magnesium atom loses electrons, it turns into a magnesium ion. So an ion is a charged atom. It's an atom with an overall charge. Atoms are by definition neutral. They're always neutral. but when they gain or lose electrons, their charge changes, their overall charge, that is. So, what magnesium actually likes to lose two electrons. You might be wondering, why does magnesium lose two electrons? Because if you look here, again, as where I'm pointing, if we lose this valence electron and we also lose this valence electrons, now we will go back to the second shell. And how many electrons do we see in the second shell? If you pause the video, you'll see we have 8, which is the magic number, which is the octet. So again, that's why magnesium loses 2 electrons to achieve the octet rule. And when magnesium loses 2 electrons, it becomes positively charged. It gets a +2 charge. Because when you lose negativity, you become more positive. So positively charged ions are also called cat ions. And that's definition. And on the other hand, let's look at what happens to non-metals. In this example, fluorine. So fluorine, if you notice, the last shell has 7 electrons. It's 1 electron shy away from achieving the octet rule. So fluorine is actually going to steal an electron from a metal, and it will have now 8 valence electrons, achieving the octet stability. When fluorine gains an electron, again, your gain electrons are negative, so you'll be gaining negativity. So because fluorine gained 1 electron, it'll have a -1 charge. Atoms that have a -1 charge are called anions. Now, atoms form ions in order to obtain an octet of electrons, as we said, and atoms either will lose or gain a specific number of electrons based on their location. If you look on the left of the periodic table, as we said, these are the metals. They're going to lose electrons. Elements in group 1, if you notice, they have a +1, +1, +1, because how many electrons did they lose? Very good. They lost 1 electron. How about elements in group 2? +2, +2, +2, +2, like magnesium, beryllium, calcium, strontium. They have a +2 because they lost 2 electrons. And if you look at group 16, these are nonmetals: oxygen, sulfur, selenium, so on and so forth. They have a -2 charge because they gained 2 electrons to achieve an octet. They had 6 before, 6 electrons in their valence shell. They get 2 more electrons, and now they're 8. Fluorine, we talked about it, similar to chlorine, bromine, and iodine. They have a -1 charge because they gained an electron to achieve stability, to achieve an octet. Ionic bonding, it forms when ions of opposite charges come together to make the ionic bond. As we said, a metal and a nonmetal. When you have a metal and a nonmetal that form a bond, this ionic bond, the compound is known as salt. So actually, there are so many different types of salt. For example, the salt that you use at home is sodium chloride, NaCl. It has ionic bonding. This salt in front of us, MgF2, magnesium fluoride, is a different type of salt. There are so many different types of salts. When you hear the word salt, you should be thinking of ionic bonding. And this all happens because positive and negative ions combine in specific ratios to create an ionic compound that has no overall charge. So you can think of the salt that you're sprinkling on your food is electrically neutral. It's not going to electrocute you if you touch it. Now let's talk about most ionic compounds. They exist in crystals. So if you look at your salt, or let's say if you went to salt mines, you'll see that they form these beautiful crystals. And if we look at the molecular level, if we zoom in, you'll notice that they are arranged in this beautiful uh, arrangement, which we call it a crystalline structure. Everything is arranged in a beautiful pattern. It's a regular pattern. Green circle, purple circle, green circle, purple circle. And we also call that a formula unit, and that's the smallest repeating anion cation pattern in a crystal. And that's called a A crystalline structure. The textbook mentions in the nature box section, should we use silver nanoparticles to reduce body odor? And they saw that fungi and bacteria cause offensive odors, and it's already been studied. Now, the silver nanoparticles actually have antifungal and antibacterial properties, and that's why they were thinking of introducing these nanoparticles to reduce body odor, kind of like a deodorant. Nanoparticles, the nanoscale is very tiny, so these are particles between 1 and 100 nanometers in diameter. Many clothing products are infused with silver nanoparticles, if you see on the right. But the real question, and the question that we should be asking, how do these nanoparticles kill bacteria and fungi? So we have to look at the bonding, and we have to dive deeper into the interaction between all these particles, chemical particles, chemically synthesized, and living organisms. Again, it continues and it tells us that silver atoms, which are represented here as Ag is the symbol for silver, they become ions. Notice, not just any ions, they become cations because they have a positive charge in the presence of air. They become oxidized and they lose an electron. And these silver cations now are toxic to fungus and bacteria. So if you see here, this is a control. This is egg water. This you can see the condition of it before we add the silver. Notice what happens as soon as we add the silver. It shrinks. So this shows that silver ions are toxic to fungus and bacteria. Clothing embedded with silver will lose its ability to kill fungus and bacteria after a few washes because the silver is used up and we have to replenish it somehow. Now let's talk about covalent bonds, the second type of bond, which is very important. So again, some elements participate, again, not some, all elements that participate in bonding do so in order to become stable. Now, for covalent bonding, we have two nonmetals. They come together, but instead of losing or gaining electrons, they do something completely different. They start sharing their electrons. So, covalent bonds occur when electrons are shared between two atoms. We're going to learn sometimes the electrons are equally shared, and we call that nonpolar covalent bonds, and sometimes the electrons are unequally shared. One element hogs the electrons more than the other, and we call that a polar covalent bond. So again, as we said, polar covalent bonds occur between nonmetals. Now there is a special type of covalent bond that occurs when you take these elements that are highlighted here: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When you take these elements and you link them to themselves, for example, if you have two hydrogen atoms bonded together, two nitrogens, two oxygens, two fluorines, you get a special type of molecule that's called a diatomic molecule. The prefix di means two. So these are two elements or two atoms that are bonded together covalently to make a diatomic molecule. Now these molecules obey the octet rule. They have an octet and they're very stable. And if you actually look in nature for these seven molecules, you are not going to find them by themselves, or atoms, I should say. They will always be in a pair. So one, two, three, four, five, six. These seven, yes, seven atoms will always be in a pair. So you're never gonna see hydrogen just a single atom of H floating. It will always be linked to another hydrogen covalently. And oxygen, the element that's responsible, you know, for our breathing. Oxygen, O2. See, it's O2 because it's two oxygen atoms covalently linked together, and they're happy. They have the octet. They have an octet. Definitions that I talked about, but here's the definition. When we have a covalent bond, atoms of the same element are nonpolar because they share the electrons equally. So there is no lopsidedness. Yes, it's a long word in electron sharing. No lopsidedness. Yes, yes. So having no lopsidedness. So it's not polar. So the electrons are not shifting to one side or the other. Everything is in the middle. Versus covalent bonds, covalent, which is, if you look below, this is water. The electrons are shared unequally. Actually, if you look at this, you can think of it as a heat diagram. The electrons are spending a lot more time towards the oxygen end than the hydrogen end, and that's why water is a polar covalent molecule. It's still a covalent molecule because oxygen is a nonmetal, hydrogen is a nonmetal, so they are sharing the electrons, but the oxygen is just keeping the electrons a little bit more towards itself. So that's a polar covalent bond. And the reason why is because oxygen has a higher electronegativity value than hydrogen. That's why it's keeping the electrons more towards itself. So the three types of bonds that we talked about, ionic bonding is between a metal and a nonmetal. The electrons are completely transferred from the metal to the nonmetal. The second, and that's the most polar, by the way. The the next type of bond that we discussed was the covalent bond. Covalent bond that is polar. The electrons are shared, but they're shared unequally. So the element with the greater electronegativity, and in this example, element Y, will share the electrons a little bit more towards their side than the element with the lower electronegativity value, which in this case is element X. And the last type is when you have a covalent bond that is nonpolar. So the electrons are equally shared between the two elements, and this is considered the least polar of the three. Ionic bonding is the most polar because the electrons are fully transferred from one atom to another. The last type of bonding we're going to be talking about is metallic bonding. And you guessed it, metallic bonding occurs between metals. So this is the bond within a pure chunk of metal. And the electrons form a sea of negative charge. You can think of it as literally the sea or the ocean, and we call it a sea of negative electrons. When metals bond together, their electrons become delocalized, which means they can move between the atoms freely. They can move between the metallic atoms freely, and they make a sea of negative charge, and the electrons move through the whole lattice of cations. They're not localized to their atom. They're going to shift, and that's why metals are malleable and they conduct heat and electricity. uh, the sea of negative electron is what allows that. We discussed the word electronegativity. So let's define it. Electronegativity is the tendency of an atom to draw electrons towards itself or to attract electrons towards itself. And very importantly, in a chemical bond. So when two elements bind, the ability of an atom to attract electron, you can think of it as a magnet, is called the electronegativity value. The most electronegative element on the periodic table, 4.0, you can think of it as the element with the highest GPa. It's the biggest magnet, is fluorine. If you put fluorine, for example, with sodium, fluorine is going to steal sodium's electron completely. It has a strong enough magnet to completely attract sodium's electron. When you the difference in electronegativity value could help us determine the type of bond. So this is another check for us to figure out the type of bond. So for example, if the electronegativity difference is very big, let's say bigger than 1.7, we would say the bond is ionic, which is pretty much between a metal and a non-metal. Um, And if the difference is moderate, for example, between zero point 0.4 and 1.7, we would say we have a polar covalent bond. And if the electronegativity difference between the two elements is less than zero point 0.4, we would say we have a non-polar covalent bond. So subtracting electronegativity values of atoms is also a mathematical way for us to figure out the type of bond at hand. Green Beat, which is a section in your textbook, collaborative consumption. So they say that the forming bonds between humans. If you see the label here, collaborative consumption, you got items such as pasta maker. This is kind of like a gift that you're sending someone. And a U.S. citizen use 10% of the things in their garage once a month, believe it or not. And collaborative consumption promotes sharing of common items among many people. So this shows that this is a tag that you could use to share items with other people. This idea saves energy and resources, and the Open Shed website allows neighbors to share items. And the textbook gives us the website www.rightster.com, which is a ride sharing site. And Ego Car Share rents out cars. And the last point they mention is that millennials are most likely to invest in collaborative efforts. So the shift is collaboration, and which is good. But and the question that arises is, how likely are you to participate in each of the following sharing programs: car sharing programs, and home or vacation sharing programs? And they broke it down by demographics, and you see that younger people they want to share more, than older people are less likely to share. Thank you for listening to the lesson, our chapter 4 summary. The next steps is to complete the quiz posted on Brightspace. Email me if you have any questions. Thank you and see you soon.